Light, Part 3. So in this video we're going to look at some different interactions of light with different things. We'll get into the idea of 3D movies, how those work, and rainbows. So first we'll start off with transparent materials. These are things basically we say we can see through. Light travels through in nice straight lines, described as something that is clear. That doesn't necessarily mean that all of the light passes through. Oftentimes you'll see the definition of this that says all the light passes through it, or nearly 100%. That's not true. We have something such as a red filter or a green filter, different colored pieces of glass or plastic or something of that nature. For example, like a red filter would only let the red light through, and that's not 100% of light coming through, but it does come through in straight lines, so it's essentially like looking through a window. So we describe that as something that is transparent, where you clearly see the object on the other side as it is, as if the material was not in between you and that object. So here's an example in this center, this little section here that's wiped off this window. You can see clearly the trees in the background, but the surroundings around that and everything you can't see clearly through. This is what's known as translucent. You can see some of the light coming through, but you can't see clearly what's on the other side. And so translucent materials lets the light come through, but generally not in straight lines. So as a result, your object is blurry. If you remember, we looked at how the eye worked. The light comes through and it would focus on one point on your retina. Well, what happens when the light doesn't come through in straight lines is it doesn't focus in one spot, and so that's what looks blurry for you. Same thing happens if you have poor vision and you have blurry vision. It's because the light that's coming through your eye doesn't all focus into one point. So again, the light source is usually not distinguishable there, and some examples of things that you might be looking at is translucent. Your skin is translucent, and you can prove this to yourself quite easily if you think about it. Why does the sun bother you, or someone coming in your room and turning on a light early in the morning bother you? Because when your eyes are closed, because the light can still get through. Your skin is translucent, so you're still able to observe the light coming through. The last kind of material that we're dealing with here are opaque materials. Opaque materials basically block all of the light, either by absorbing or reflecting off in different directions, but they do not allow the light to pass through. You can't see through it in any way, shape. You cannot see through opaque materials at all. Now, all the definitions that we've just mentioned are based on the visible light. It's based on what we see. That's how we've defined these terms. We define the different materials, whether they're transparent or opaque or translucent. But the transparency does depend on the specific frequency or which part of the electromagnetic spectrum you are in. So glass, for example, is transparent to visible light. We're quite familiar with that. But it is very opaque to ultraviolet and infrared. Like 95% opaque to the ultraviolet in most cases. So essentially, when you're talking about ultraviolet light, if you're in a car with the windows rolled up, you're not going to get a sunburn. The ultraviolet light is pretty much just completely blocked out. Also, the infrared being not able to get through it. This is how a greenhouse works. This is what happens in a car as well. Visible light comes in through the windows, gets absorbed by the materials inside the car, which then gives off infrared radiation, the heat that we feel, and it can't get out through the glass, and so it builds up inside there, which is why the car gets so hot. Even if it's in the winter or a cooler time, it's just all that infrared radiation builds up inside there. Clouds are typically, we say, opaque, maybe translucent with visible light. We don't really see through them. We maybe see some light come through them, depends how thick or thin the clouds actually are. But clouds are pretty much transparent to ultraviolet light. Yes, you can get a pretty good sunburn when it's cloudy. Probably get a worse sunburn because you don't feel warm, and we tend to associate the warmth with the idea of being burned, so we don't think about a sunburn when it's cool or cold in that. But yes, the ultraviolet light comes through the clouds quite easily. Let's see, what else we have? Oh yeah, your walls in your house, right? Those are opaque to visible light. I think we'd all agree we don't see through our walls. However, they are pretty much transparent to X-rays, radio waves, right, and microwaves. And again, evidence for this with the radio waves is quite simply you can have a radio in your house and you can tune a station and still hear it. Same thing with television with waves coming across through the antenna. microwaves, your cell phones. All right, use the microwave range to send signals, and you can probably get signals just fine through the walls of your house in most cases. Polarization. So light that comes from any kind of a source is a transverse wave, and it vibrates at all different planes. So we kind of look at a three-dimensional idea here of the waves. And this would look like coming head on. You can see they're vibrating horizontally here, vertically here, in between. And so you have all this different random orientation of the actual waves themselves, the sort of the crest and the trough that goes with this. Polarization then is causing those waves to all line up together. So of all that random orientation that was coming through, we can use a filter that will then only allow, for example, the vertical to come through, or you could turn it 90 degrees and we can have something that only allows the horizontal through, or whatever angle you happen to be at, but they'll all be lined up with each other specifically. So that would be polarized light that comes through there. And natural polarization that happens would be non-metallic surfaces. The light then is going to be polarized parallel to the surface itself. So light coming down from the sun hits the road and bounces off it, reflects off it, will actually reflect off polarized parallel to that surface. So you see this, say this horizontal light comes through or comes off of the surface of the ground. We can use then polarized sunglasses and turn them perpendicular to that, and as a result the light reflecting off of the ground will actually be blocked out. That light that is blocked out, that is polarized in this case, is what we refer to as glare when you look at something. So here's an example of the kind of blocking out of the light. First, a couple of polarizers, and we just simply rotate them perpendicular to each other, and as a result the light's blocked out. So you can tell, okay, before they're turned, you can see the lamp in the background here, and as you rotate it, the light coming through here is horizontally polarized. You can see little arrows right there, and this one here is now vertically, and so those are perpendicular to each other, and you see how it's blocking out the light that's coming through. So here's some examples. Here's a picture taken from inside a car. No polarization whatsoever. You can see the glare on the inside of the windshield here. With the polarizing filter placed over the camera lens, you no longer see the glare. Right? So you can tell very quickly the difference, what's happening in here. Here's another example here. This particular windshield is the main focus. Nothing's polarized in this photo. And the next one, you have a polarizing filter. If you notice the windows back here as well, you can see the same effect that takes place. There's a change in the lighting that you observe because of the filter that's placed over the camera. Here's some leaves. It's the main thing I want you to see here. They're non-metallic, and the light's reflecting off them, so you can see kind of the light reflecting off all the leaves. We put a polarizing filter over it, and the brightness of those leaves you don't see anymore. Right? That's the glare that's been blocked out. Something else you might notice here in the background, without the polarizing filter, the sky is just a nice solid color looking. With the filter, you can actually see there's some clouds up here in the blue sky. Turns out the light that you see in the sky is polarized. Right? The light coming directly from the sun right around that area is not, but the reason the sky is blue is because the light is being reflected off of the particles in the atmosphere, which scatters off mostly bluish green light, right, mostly blue, and as a result you see that particular color. So with the filter, it kind of blocks out parts of that polarizing, so you lose some of the glare essentially that's there in the sky. Last one here, a lot of times people that fish or out on boats a lot and everything will wear polarized sunglasses. You see the glare on the water without the polarizing, and we put the filter over it and it reduces the glare tremendously. You can actually see the details of the rocks under the water as opposed to just the glare on top of it. So another use of polarization you probably run across when you've gone to see a 3D movie. This is a camera for filming a 3D movie. You notice there are two lenses, and they're set about the same distance apart as the average human eyes. The idea is to film the movie from both perspectives, from each of your eyes. So you see a different perspective with each one. You can also notice there's a little slightly different coloration on each lens here. It's because each of them has a polarizing filter oriented opposite of each other. So it'll film it through those polarizing lenses. Only that particular polarized light will come through. In the case of 3D movies, it's usually what we call circularly polarized. And we play back the movie with the two different, essentially two different movies. You would look at it without the glasses, you would see the images offset from each other. And as a result, it wouldn't look like anything but a big blurry mess as you do it. But if you're looking through a pair of polarized 3D glasses, one eye is going to be polarized clockwise, and the other is going to be polarized counterclockwise. And so they only allow the light to come in from each of the lenses. The original filming took place, and as a result, you see the two different perspectives through each of your eyes, which gives you your depth perception that you have for 3D. Refraction is something you may have seen before. Say you have this light beam here coming in from air into a piece of glass, and it bends. And so refraction is when the light bends because there's a change in speed that takes place when the light goes from one medium to another. It's going to travel faster in the air and then slow down as it passes through the glass. So general rule is that the light going from fast to a slow medium will bend towards the normal line. Now the normal line is this dashed line right here that is perpendicular or 90 degrees to the surface. So we always want to measure our angles as we move forward into optics and stuff. We want to always measure our angles in here from the normal line to the object. All right, and so the basic rule here for refraction is then if it is going to slow down, it's going to bend towards the normal. So instead of going straight along this path, it bends towards the normal. And the opposite happens if it slows down. Right, so if you can imagine just changing the direction of these arrows, if it goes from the glass back into the air, it bends away from the normal line here. Here's an example of something else that bends or refracts as it changes speeds. Right, so here we put a piece of carpet in here, and you'll see that the cars, as they drive along, rolling down that ramp, turn just like the light turns. It bends towards the normal, and then it bends away from the normal. So here we have an example of a pencil in water. It's in the air up here, and it's under the water down here. You look straight on, no real major issues going on here. But if you were to move off to the left side of the container to look at the pencil, you would notice a change take place. You would notice that it looks like the pencil is now over here in the water. Even though you can see in the air, it is still up here in the same spot. Alright, so we're going to look at what's going on there. Again, the light here is coming from the pencil in the air. Down here it's coming from the pencil under the water first. So if we take a look at that in a little bit more detail, say we look from above, and we got the pencil sitting there in the container of water, and you're sitting straight in front of it. So this is when we looked at it at the beginning. The light coming through the air only comes straight to you, and the light coming through the water and then into the air also comes straight to you. Remember, the rule is when it speeds up or slows down, it bends towards or away from the normal. In this case, it's coming right along the normal line, so it can't bend towards it or away from it. You don't see any bending at all. It just speeds up when it leaves the water. So you see the pencil, you know, in the same place, no difference whatsoever. But again, as I said, if you move over here to the left to observe it, you see the pencil over here off to the right. And so again, the light coming just through the air comes straight to you, and you see the light that comes from the water to come along this direction, and it bent at the actual boundary right here. So it actually came along this direction and bent this way to what you can see. Now there is light that did come along that same direction as it did in the air there, but when it got here it bent away, and so you don't see that light. It's not coming towards you. But the light that you see, right, it looks like it came from a point back here or over to the side in the water. So that's why it looks like the pencil in the water is over here, even though in the air above it's still in the same location. This clip I want to show you an actual refraction of the light. We can see the aquarium here has got some water in it, and the light is back here on the back panel of the aquarium. You can see the refraction here. But we actually played the clip and we'll zoom in on a little bit. You can actually see then the light coming in and hits the surface and it bends towards the normal. Alright, go back to that. So it bends towards the normal and you can see it moving towards it there. Now there's a mirror down here at the bottom as it shows, and so the idea is for the light then to reflect back off this mirror here, and again you can watch the refraction that takes place. Again, straight up, there's no bending noticeable. Again, as it comes back around to where it came from, it basically just follows back along the same path, and this time it bends away from the normal line. And watch what happens as you keep on bending. It keeps bending farther and farther away from the normal line. You saw it right there. Alright, it keeps bending away, and eventually it's going to bend so that it's parallel to the surface, and when that happens, it actually reflects off the surface. It actually can't get out. And so this is what's known as total internal reflection. Alright, when the angle is too steep, going from a slow medium to a faster medium, the light can actually get reflected back into the medium and not be able to get out. And that's what you're observing right here. So if you were over here in the bottom of this aquarium, you would see the light hitting you here, but it would reflect off the bottom of the water, it hit the mirror, go back out, you would actually see the light source still. It's right above you, but you look along this direction. If you look straight up to see that light source, you actually would not see it. I'll show you that here in the next clip. So here's a lady sitting by a pool. This is what I call my my horror movie version of physics. Did you catch the size of that camera? That's good stuff right there. So this guy's in the bottom of the pool. Here it is. So he's looking up from in the water, up at the lady sitting on the side of the pool. Her feet are in the water. That's why they look darker here. So the water's absorbing some of the light. And so right there, the lines is where her feet are actually in the water. It's the surface there. And so the camera is looking up at the lady there. And he's simply going to swim backwards. And as he does so, you'll notice that she starts to disappear. Her feet are still down here, actually up under the surface of the water. That line right there is the surface, and that's a reflection of her feet. So those are her toes right here that are reflecting off her toes right there. And you can see it over here on the side as well. This big circle on the side of the pool right here is being reflected on the underside of the water there. You can see the water moving around, so you can see that motion going on there. And so the camera looking up can't see her, but as he swims in closer back to the edge of the pool, you see her come back into the field of vision again. Alright, again, there's her water surface, and this is just another version of this one, but this time the camera's going to look almost straight up out of the water here when he gets far enough away, and looks up. So you can see here she's still up. It looks like she's up way up over here, when in actuality, remember where her feet are. Her feet are way down here, but it looks like she's way up there. Again, that's just the refraction of the light itself. So remember, light's the only thing you can see, and so if it gets bent at some boundary or for some interaction, all you see is the result wherever it looks like it comes from for you. So it looks like she's coming from way up here, even though she's actually sitting right here on the edge of the pool. So again, this is that total internal reflection. So you can see this underneath water in a pool yourself. Look on the underside of water in a glass, clear glass that you have, and you can see it there as well. Here's a more up-to-date picture from underneath a modern pool, and you can see the edge right here is where the edge of the pool is in the surface, and you can see the reflection. That's the bottom reflecting off of the water there, and up here straight ahead you can see the lights in the ceiling there. Index of refraction, that's just a lowercase n. That's just a way of measuring the speed of light through a given medium relative to the speed of light. So it's just the ratio of the speed of light, which we know to be 3 times 10 to the 8th meters per second when it's in a vacuum, and divide that by v, which is just the speed of light through the particular medium. The larger the index of refraction is, the slower it is, and therefore the more it is going to bend, the more refraction you're going to actually observe. So air is pretty much an index of refraction of 1. It's not exactly 1. It's a little bit slower than a vacuum, but it's pretty close, so we use that as an estimate. So different colors of light. This happens for all light, but we're specifically going to focus on visible light here because in the end I want you to see how the rainbow is formed. The different colors of the visible light have different speeds when they go through different materials because they have different frequencies. So I have this animation here to kind of give you an idea of this. A little slider down here, we're going to change the refractive index of the material. Right, so right now it's set for a vacuum or air at 1, and you can see the waves themselves and kind of pay attention to the length of those waves. Right, so the wavelength is related to the frequency. It's inversely related to the frequency, and as it gets longer you have a lower frequency, as it gets shorter you have a higher frequency. So as we play this little simulation here, as we increase the index of refraction, we get to a point here you can see that the wavelengths here have gotten shorter, all right, and than they were out here. Now it's traveling slower in here and has the higher frequency. Right, so the different speeds are frequency related within the material, and then when it comes back out it goes back to its normal wavelength, frequency, and the full speed of light. So we keep increasing the index of refraction, make it a little bit more noticeable. Watch the wave speed passing through the material. See, it's going noticeably slower, and it's noticeably higher frequency. So you can go back and replay this to look at it, but basically what it's showing is the higher frequency wave is going to be traveling at a lower speed in the material. So if we apply this to the visible light that we see, I have a couple of animations here. Here's one that shows a prism, so it's a piece of glass in a triangle shape, and the light comes in and the light refracts and bends. You can see it all bending, but you'll notice then that the red, which is the lower frequency, is going faster and it doesn't bend as much, and the violet is the higher frequency, going slower, bends much more. You can see the separation here. The reason we do this with a prism is because in order to see the actual light separation you have to have two refractions at different angles to spread out the light so our eyes can actually see the different colors. This animation just shows more of in a photon form of the same thing, but I think it's a little bit easier to see. You can see these lines here kind of bending, and as they're traveling through the material you can see the refraction that's taking place overall, but you can then see the spreading out much clearer there. Alright, so here we are. Here's the rainbow. Specifically, there's a double rainbow in this case. Now notice the shadow here, that's important as well. In order for a rainbow to form, the observer has to be in between the light source and the water source. In this case, the moisture in the air, when there's rain over here, or whatever it might be, just maybe some droplets or whatever, mist. But you'll notice the rainbow, typical rainbow, you have the red on the top here, and then you have the violet on the bottom, pretty obvious right here. But the double rainbow is the opposite of that. If you look at it closely, you see the red on the bottom and the violet at the top here. So here's what's happening. Alright, so here's the observer, so we're looking from the side now, and all these rain droplets over here in the distance, these two down here represent the primary rainbow that you see right here, where the light comes in from the sun, it goes into the raindrop and refracts, and then it hits the back side of the water droplet and totally internally reflects, and then it comes to the other side here and actually refracts again. So you get the two refractions like we saw with the prism, and so that happens here, and that gives us the primary rainbow that we see right there. Now there's other light that's coming in at different angles, but it doesn't do this total internal refraction. It just hits it and refracts and then goes back on out at different angles that you have. So it takes a specific angle as are noted here. The secondary rainbow, right, or the double rainbow, happens at a slightly different angle where the light comes in such that it reflects inside here twice. You get two total internal reflections before it refracts out. So it spends more time in there, which is why it's darker. If you look at it, it's not as bright as the primary rainbow there, and it flips over because it's bounced around now, and so the light's flipped around opposite of what it was over here. So that's where we get our rainbow from. If you look at the shape of the rainbow closely, you see something interesting maybe that you weren't aware of here. If you make your own rainbow in your yard, notice the shadow here again. The sun's back behind the observer, and then the water, out here is being sprayed out in front. And you can do this, with your own water hose, and you spray the water around, and you notice it follows around in a nice circle, right? Rainbows are actually circular in shape. We just don't usually see the whole thing all the way around. We just see parts of it. All right? We see a little piece up here, a little piece over there. All right? We might see just this section right here up in the sky. We might just see that, but it's actually a circle, and you can see a little bit of a double rainbow here as well on this one. One more example of this. This is in Toronto. It's on the shores of the lake, and you have a rainbow here. Alright, so you notice the shadows. The sun's back behind the tower in this case. It's the CN Tower in Toronto, and you can follow the rainbow all the way around. So this is a continuous circular rainbow, which you don't usually see much because we're much closer to the ground usually, and so we don't see the bottom parts of the actual rainbow there. And so that's how we get the rainbows. And that will wrap it up for our light explorations and ideas for this year. We'll continue on with optics next week, but I hope you enjoyed some of the more interesting aspects that we have when we talk about light.